Let's take a look at what happens when we mix two acids together and how we determine the resulting pH from that. So here's the biggest tip before we start. It says always start with the stronger acid. We need to track the H pluses. We need to see how much H plus, because we're dealing with acids, is resulted in the dissociation of each acid when mixing them together. So by using the larger K first, that's the stronger of the two acids because it dissociates further to the right. It favors the products more. We are going to account for the majority of the H plus being distributed immediately to the right. So here is the example that we'll look at. It says find the pH of a mixture of 1 molar HCN and 5 molar HNO2. So by looking at that, you should notice something right away. I have two K values. Specifically, I have 10 to the negative 10th and 10 to the negative 4. This one is my stronger acid because this is a larger K. So I'm going to utilize that first. So we are going to do some ice boxes, but we're going to make them really small. I want to make them on the left side so I can do the work on the right side. So here's my first ice box to just help me organize my information. So it says that I have 5 molar for my first acid. Again, technically, I'm taking two acids and I'm pouring them both into one solution. But we can't approach it like that. We need to kind of say, okay, if I have one acid, how much does it dissociate? And then when I have the other acid, how much more does that dissociate into my solution in terms of my H+. So the first step is fairly straightforward in terms of ice boxes because it relates and reflects the things that we've been working on. So I now just make this expression equal to my K value, as always. And you'll notice that my value is greater than 100, so I don't have to worry about my ability to cross out this X, but I will prove that anyway. So my X, which right now is my H+, equals 0.0447 molar. Okay, if you were worried about if you could cross that out or not, what you can do is just on the side is take that initial or that value of X over the initial amount that you had, and you can see what that value results in. After converting it to a percentage, that is 0.89%, which is much less than 5%. So that's good news. So that's my H+. Now, if I was just asked what is the pH in the resulting dissociation of just the nitrous acid, the HNO2, I could just do negative log of that. But that's not what it's asking. It's asking what is the pH of this mixture. So now, if I take the second acid and I dissociate that, this is where an icebox is actually extremely important. First one, maybe not. Maybe you'd recognize that it is x squared over initial minus x. But here's the difference. I'm starting with 1 molar of HCN, but I don't have simply zeros anymore. Okay, I have an amount of my H+. This is floating around in solution right now. So I need to include that. I'm tracking my H+, and now that is 0. Because this value is still 0, I know that this gains, the CN minus the cyanide, will be gaining because I need to produce it, and that means the reactants will be losing concentration. And then I let the icebox work for me. And now I make this equal to my second K value. So you just have to make sure that you are plugging this in correctly. So this is now my expression. Now, luckily, these are all 1-to-1 ratios, so I do not have to worry about this. Now, because my k value is so small, I don't really need to worry about distributing all of my x's. Okay, I can cross off things that are added or subtracted because my initial amount, 1.00, is clearly 100 times larger than the 6.2 times 10 to the negative 10th. So now I can solve for this. Now, here is one little trick. I cannot say x equals h plus anymore because that's what that's what h plus equals. So now I need to just be a little more careful. So I'm going to solve for x, and it equals 1.4 times 10 to the negative 8th. So now I want to solve for h plus, which will get me to pH. So it's very important that you have the relationships correct. So h plus is 0.0447 plus x, which is 1.4 times 10 to the negative 8th. Fortunately or unfortunately for us, that second value is so small that it really doesn't help us very much, and it's not going to change our values. So my final concentration is still going to be 0.0447. Some problems will actually say that you can ignore one of the acids or another. But now I finish this off by taking the pH of my H concentration. Which results in a pH of 1.35.